Okay, so limits at infinity. I know we did this yesterday, but I just want to put it up again and capture it for anybody who wasn't in class. So the graph of y equals 1 over x, when you put it in the calculator, it looks like that. And we recognize as x goes out to positive infinity, y gets really, really, really small. Yeah, I know. You've done this. I'm just filling it in. So the limit as x approaches infinity of 1 over x is in fact 0, and then in some books you'd see 0 plus to say you're on the positive side of 0. And then as you go out to negative infinity, as x approaches negative infinity, y gets really small, and we recognize that it's on the negative side of 0. Okay? So then the next thing that we did was define what a vertical asymptote is. And in high school and in grade 11, we didn't really define it in this way because, well, you weren't ready for the whole idea of a limit. So the horizontal asymptote is when you approach infinity and it approaches some number b, or if you approach negative infinity, you approach some number b. And then we graphed y equals x over x squared plus 1, and we said the graph looked like this. And we recognized that the highest the graph got was positive 1, and the lowest the graph got was negative 1. So we made a limit statement. As x got really big, y got really close to positive 1, and as x got really small and negative, y got really close to negative 1. So you're just using your graphing calculator for that. Confirm numerically, you just stick a really large number in for x. As big as you want. How big? As big as you want. Okay? So you could put 1,000,000 in for x, you could put 100,000 in for x, you could put 23 in for x, and well, it'll give you an indication of what's going on. Okay? So that's what we did yesterday. Flip the page. So when we graphed sine x over x, we were interested in it a couple of days ago. We were interested in what it looks like as it got close to 0. We learned that the limit as x approaches 0 of sine x over x was 1. This was a big property that we learned about a couple of days ago. But now what we're interested in is what happens to the graph as you go out to positive infinity, and what happens to the graph as you go out to negative infinity. What happens? Look at the graph. What happens to the y values? Are they getting smaller and smaller and smaller? Yeah, but look at the y values. Are they, I mean, it's going up and down over the x-axis, but is it going as much up and down over the x-axis? Maybe we need to just put it in the calculator and show us. So as x is getting bigger and bigger and bigger, what's happening to the y values? They're oscillating. Here's the word, today's word of the day, oscillating over the x-axis. But look at what's happening to them. They're getting smaller and smaller and smaller. So small they might as well be 0. So the limit as x approaches positive infinity is 0, and the limit as x approaches negative infinity, because it's exactly the same on either side of the graph, it's 0 as well. Okay. Confirm numerically. I'm going to let you do that on your own. Stick a really large number in for x, and you'll recognize that y value is very small. Analytically, now here's where it gets a little bit interesting. Yeah, sneaky sandwich. It's called the squeeze theorem. Okay. So we're going to take a statement. We're going to take what we're working with. We're working with the limit as x approaches positive infinity of sine x over x. I'm going to do this kind of like an English paragraph, but with a whole pile of math symbols. Someone tell me about the range of sine x. What is it? Between -1 and 1. We need to know the range of y equals sine x. And you just said to me the highest sine x gets, no matter how we graph it, the highest it gets is +1, and the lowest it gets is -1. Okay? Therefore, 1, 2, therefore, the limit as x approaches infinity of sine x over x has to be between the limit as x approaches infinity of -1 over x and the limit as x approaches infinity of +1 over x. What did I do? Pardon me? Zoom out a bit so you can kind of read. Yeah. So we start with sine x. And the reason we start with sine x is because sine x oscillates. It goes up and down over the x-axis. And it goes up and down over the x-axis the same amount every single time. We like that. You could almost picture those two yellow lines as a tube of toothpaste. Okay? What happens as you push the toothpaste out the end of the tube? Don't do this at home. Your parents will smack you one. What are you doing getting toothpaste all over the counter for? But visualize a tube of toothpaste. As you squeeze the toothpaste out, what happens to the foil end? They get closer and closer together, do they not? Well, what I'm doing is saying the highest the tube of toothpaste can be is +1, and the lowest the tube of toothpaste can be is -1. So what I can do is write it like this. The limit as x approaches infinity of -1 over x is between, or sine x over x is between -1 over x and +1 over x. Okay. What's -1 divided by infinity? -1 divided by infinity. You have -1 divided by 7 gazillion. A really, really small number. So -1 divided by infinity is 0. 0. Okay, what's +1 divided by infinity? 0. Okay, now, you tell me a number. You tell me the only number that is bigger than or equal to 0 and less than or equal to 0. There's only one number that has that property, 0 itself. Therefore, the limit as x approaches infinity of sine x over x is 0. Now you're thinking to yourself, whoa, that was kind of weird, wasn't it? Yeah? Okay. We're going to go to Neverland and we're just going to do another one together. Okay? What? That was too fast? Okay. Okay, so there's the question I want you to figure out. So the first thing you have to do is just think about y equals 3 cos x plus 1. What's the highest? What's the highest this graph gets? 4. What's the lowest this graph gets? -2. So this statement can be changed into okay. What's -2 divided by infinity? 0. What's +4 divided by infinity? 0. Oh. Tell me a number that's bigger than or equal to 0 and less than or equal to 0. Now, it's not always going to be 0, so don't make the assumption that that is the case. But what I'm trying to get you to do is to tell me the highest that the graph can be and the lowest that the graph can be. Devin. Pardon me? Okay. This is going to be really contrived, but here's one where it's not 0. So the limit as x approaches infinity of sine x over x plus 1. So y equals sine x is between the range is between -1 and +1. So you get limit as x approaches infinity of -1 over x plus 1. So what's -1 divided by infinity? 0. Plus 1 is 1. It's still really arbitrary, but +1 divided by infinity, 0 plus 1 is 1. So you tell me a number that's bigger than or equal to 1 and less than or equal to 1. So all I'm doing graphically, all I'm doing is taking a function, and this is going to seem kind of weird, but I'm taking a function that's doing something really cool, and I'm squeezing it between two known values. And you could picture this as a tube of toothpaste. Those blue lines are your tube of toothpaste. All I'm doing is pushing the toothpaste out the end. What happens as I go out the end? These values get so small that they might as well both be 0. And that's what the squeeze theorem does for you. Now, it's really kind of cool. Later on, the function still could be doing some really cool things, but it might not be going to 0. I've seen ones in university where we actually squeezed the function between two exponential curves. It was kind of cool. We squeezed it so that the function was squeezed between y equals 2 to the x. So we had something that always a little bit bigger than y equals 2 to the x, something that was a little bit smaller than y equals 2 to the x, and all we did was squeeze it between them, and lo and behold, it became y equals 2 to the x. So it can get used in a variety of ways. It doesn't have to always be just a number. It can be squeezed along anything. That tube of toothpaste can look really cool. Okay, it doesn't have to be just a horizontal toothpaste. It can be, you know, like a banana toothpaste. And you know, comes the toothpaste. Okay? You get the idea? I don't know, a friend of mine calls it that. That's not my terminology. Okay, so properties. The same properties hold true. If you add the functions, you can add the limits. If you subtract the functions, you can subtract the limits. If you multiply the functions, you can multiply the limits. If you multiply the function by a number like 2, you can multiply the limit by a number like 2. You can divide the functions, you can divide the limits, as long as you don't divide by 0. And if you square root the function, you can square root the limit. Or you square the function, you can square the limit. Yeah? Okay. You guess? You want an example that for these, or you're going to do it naturally anyways. It's quite funny. Like, here are these rules. Well, when you're working with them, you just do it. Okay? I'm not going to say, which rule did you use? I used rule 6. Okay, so using the property of limits. The limit as x approaches infinity of 5x plus sine x over all over x. So, I have two fractions with a I have one fraction with a single monomial denominator. You tell me something that's really cool that you can do with single monomial denominators. You're like, what? 1 plus 2 all over 3 can be written as 1 over 3 plus 2 over 3. A single monomial denominator. So, you can write it as the limit as x approaches infinity of 5x over x plus the limit as x approaches infinity of sine x over x. This is my favorite chapter in the course because you can equals everything because they are all equal to each other. The only place in this course where you're allowed to have run-on sentences. Right? If you were in Math 8 and you did this to me, I would throw you against the wall and hit you with a 2x4 repeatedly. And I would feel good about myself. The x's cancel, and you are left with the limit as x approaches infinity of 5 plus the limit as x approaches infinity of sine x over x. Okay. This is kind of a stupid question, but what's the answer to this? 5. There is no x, it's just 5. Okay. We just did this. What's the answer to that? 0. And 5 plus 0 is, in fact, 5, and we're in our happy place. Okay, you do the same thing for b, please. So what'd you get? 3. Yeah. The limit as x approaches infinity of 3 is 3. These are my favorite ones. You just write the number down. Okay, ready? The limit as x approaches infinity of 1 over x squared. Okay, if 1 over x is 0, 1 over x squared is really 0. Right? Yeah? Like 1 over infinity squared? Blow your brain away. Well, if 1 over infinity is 0, what's 1 over infinity times 1 over infinity? Oh my God, it's really 0. Really 0. You know what I mean? Really 0. Mom, we learned about 0, and then there's really 0. It's 3. Okay, Devin, question. Yes. Yes, it does. It gets to infinity x times as fast, but it still takes forever to get there. I know. This is your brain. This is your brain on infinity. Any questions? Oh, that's even faster. Okay, next one. You're getting to listen about infinity. How is that going? Okay. As x goes to infinity, 1 over x goes to... Okay, folks, answer that question. Okay, I'll mark it and I'll let you know Monday. Yeah. Okay, as x goes to infinity, what happens to y? As x goes to infinity, what happens to y? Hey, folks, let's do this. Goes to 0. So what happens to, what is the cos of 0 then? Cosine, as x goes to infinity, 1 over x goes to 0, so the cosine of 0 is 1. That's how you do that one. Okay. So, what we need to talk about, what else do we need to talk about? Oh yes, vertical asymptotes. So, the graph of y equals 1 over x looks like this. So we say as x gets close to 0 from the right-hand side, our y values get really, really big and positive. And as we approach 0 from the left-hand side, negative infinity. So we define in this graph x equals 0 as a vertical asymptote. And this is our proof of a vertical asymptote. So if I ask you where are the vertical asymptotes, you're going to say there's one at x equals 0, and I'm going to say, how do you know? And you're going to say, Mr. Epp, I have to write 2 limit statements. Okay? Not because my graphing calculator showed me there was one there. Okay? Flip the page. What? Proof of a vertical asymptote. It doesn't have to both. Only one of the two has to go to infinity. That's key. I can actually make functions that only have one vertical asymptote. You're like, what do you mean? You're like, what is he talking about? Well, if I draw a function that looks like, this isn't actually, well, there, that function only has the limit as x approaches 0 from the right. There is no function on the left-hand side. Okay? Last page. So find the vertical asymptotes for each of the functions, use a graph and limits to help. Okay, everybody graph y equals 1 over x squared on their calculator and tell me what it looks like. Yeah, that's why when I teach this in grade 11, we call it a volcano function. Because it kind of looks like a volcano. So we would write a limit statement. The limit as x approaches 0 from the right would have a value of infinity. And then you would say the limit as x approaches 0 from the left, it would have a value of infinity. Stupid question. Well, not stupid. Are these two the same answer? So, really? Your infinities look different. Yeah, I know. I need to practice those more. So what would you say the limit to 0 from both directions is? It's still infinity. Still infinity, because they're the same number. You only say does not exist when they are different numbers. Okay? What about y equals f of x, f of x equals 1 over x plus 1? Might floor your brain as I can do these in my head. Because I am a Math 11 god. Well, you didn't teach us Math 11, Mr. F. Yeah, I know. I want to teach Math 11 next year. Yeah, I would like to. Kids need to fear math some more. No, I need to make it harder. Positive. What? Well, because if you approach from the left and from the right, you can actually say that from both directions, dude. Because of this thing. Yeah. So, as we approach -1 from the right, we would say positive infinity. And if we approach -1 from the left, you would say negative infinity. So could we make a conclusion number 3 for that one? No, because positive infinity and negative infinity are not the same number. Yeah. -1 positive means -1 from the right-hand side. That means this. Whoop. -1 minus means from the left. Okay? Last one. Well, almost last one. Yeah, it's the way I teach grade 11s to do it. Yeah, I do. Just haven't in the last couple of years. What? 12. Math 11 is hard? It should be a little bit harder, maybe. What? No. Do you want it to be harder than Math 12? Now, I'm writing 2 down, but actually, how many should I be writing here? 6. Well, 4 probably. 6. Well, positive infinity and negative infinity are not the same, so you can't conclude that they're right. What? Well, for this one, if I asked you to talk to me about it, you would have to write all 4 down. On a test, if I asked you to give me a 10-second graph and then talk to me about the vertical asymptotes. No, there isn't 6. There's only 4. Somebody said 6 because they thought they could conclude these two were the same, so you could do the limit as x approaches +1. Well, you can't. Because that would be bad, because they're not the same numbers. So you could talk about -1 plus and -1 minus, or the other asymptote. Okay, y equals tan x. Y equals tan x. How many asymptotes does this graph have? How many asymptotes does this graph have? Infinite. So do you want to write them all down? Okay, let's just do one of them. Do you want to do positive pi over 2 or negative pi over 2? Positive pi over 2, so this asymptote right here. So your statement would be the limit as x approaches pi over 2 from the left. You would say positive infinity. And then if you did the limit as x approaches pi over 2 from the right, you would say negative infinity. Now, the fast way of finding vertical asymptotes, not proving that they exist, but for finding vertical asymptotes, all you do is solve the denominator equal to 0. So if you were given the equation f of x equals x over x squared minus 1, the fast way to find vertical asymptotes is x squared minus 1 equals 0, x squared equals 1, x equals plus or minus 1, and lo and behold, you have vertical asymptotes there. So that's all you actually have to do. The same thing with tan. Because tan is, my Math 12 students, come on, tan is sine over cos. All you're doing is finding when cosine equals 0. Well, you should be able to do that with your eyes closed and your arms tied behind your back. Cos equals 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, 11 pi over 2. Right? If you're in my Math 12 class, you should be able to do that. I have expectations. And that's where we're going to stop. So, Monday we're going to talk about end behavior models. What I would like you to do for homework is to make sure that you get a good crack into section 2.1, because one of the things I really want to talk about are questions on page 63 in the 21 to 29 variety. So if you haven't tried those, we need to talk about those, because those are so important in this section. I like questions 1 to 6 because they're fun and you get to look at pictures and talk about stuff. But the algebraic manipulation in questions 21 to 29 are of paramount importance. Okay? Very important. Don't think, F's not going to ask me about those. Sorry, folks. They're important. Now, don't be scared. They're actually not that bad. Like, I'm just trying to make sure that you don't avoid them. All they are about is, can you factor? You have to clean stuff up and factor, clean stuff up and factor, clean stuff up and factor. That's what it's really about. Okay, so you guys know what you need for homework. If you haven't turned in 1.1 to 1.6, please do so before I go home today, which is probably right around 3:30, because you know what? I'm not staying past 3:30 today. I'll accept homework late on Monday, but I will not accept homework late on Tuesday because I'm marking, because I'm going to give it back, and it's not fair to students who do their homework on time. Okay? I'll give you the weekend as the extension, but that's it. Okay? There you go. I'm done. Maybe you want to try some of that homework now. I don't know.